Hello friends, welcome to my channel. Let's have a look at problem 1202, smallest string with swamps. So in this video, we're going to share a solution based on the disjoint set data structure or union find. So the idea actually is very straightforward. So we're going to use disjoint set abstract data structure to form indices clusters. So within each cluster, the corresponding characters can freely swap with one another. We just need to sort for each cluster in order to finally get the lexicographically smallest string. So in order to better understand the problem statement, here is an example we cooked up and use it for a walkthrough to fix the ideas. For example, we have this string S is given by DAX, B, and M, and the pairs are given as here. And then we know the index 1 and 3, index 0 and 1, and index 4 and 5 can swap with each other respectively. So if we form these relations, for example, 3 can swap with 1 and 1 can swap with 0. So the three indices 3, 1, 0 form a cluster, and the corresponding characters in 0, 1, 3 are DAB. So here we do not need to pay special attention to the order because later we are going to sort. And then similarly, index 4 and index 5 form a cluster. The corresponding character are M and N. So in order to get the lexical smallest string, we're going to sort per cluster. So for example, the first cluster, if we sort, we're going to get 0, 1, 3 in the index. And then if we sort the characters, we are going to get A, B, D. So then in the final return, the index 0 will have letter A, index 1 will have letter B, and index 3 will have index D. So similarly, we can sort for the index 4, 5, so we get 4, 5, and the character after sort is M and N. So in other words, index 4 will correspond to M in the return, and index 5 will correspond to N in the final return. So with that said, let's look at the build the output step. So we just make this correspondence after sorting clusters and characters. So for example, 0 corresponds to A, 1 corresponds to B, and so on. So the ABX DMN is what we need to return. So that's actually the full walkthrough. Hopefully it clarifies all the things and fix the idea. So before we look at the code, so here are some questions. So first, we can actually try to use graph theory or graph language. So if we regard this problem as graph problem, then the cluster here corresponding to nothing but the connected component, right? So please try solving this problem using traversal method. For example, you can use breadth first search or depth first search to identify connected components. Then the remaining are the same to build the final output. So it's equally natural, I would say. With that said, let's look at our plan. First, I'm going to implement the union find class. The reason we implement this outside this solution class is to make it general purpose. After that, we're going to apply directly to the problem here. And finally, as an extra step, so we are going to make some temp complexity analysis just for fun. So if you are not interested, you can stop after we finish solving the problem itself. So with that said, let's first look at the implementation for the disjoint set data structure. So disjoint set union. So I'm going to use a class name like DSU. And then the main goal is to implement two methods, find and union. So here, in view of the constraint 10 to the power 5, so we're going to use path find with path compression and union by rack. So let's first look at the initialization. So init self. Here I'm going to introduce two attributes. One is root, which stores the node root relationships, and also the rack, which tracks the racks. It's also a dictionary. So with that side, we're going to look at the find method. The find method actually accepts a index. So here we are going to group the index to form clusters. Then we build the output. So here I'm going to use union find with path compression. First, I'm going to treat a case that is I is not added to the data structure yet. If I not in self root, for this case, we're going to add it to the data structure and use the natural default rack I so equals 1. So here the rack will be the cluster size. In this case, the return would be I, and then in the other case, so if I is already in the data structure, so we're going to make a chain of calls to retrieve the root. So first, I'm going to introduce a temporary variable called result, and then we're going to check if result and its root. So self root result, if they are the same or not. If they are not the same, so we're going to basically set result equals self root result and continue the procedure. So in between, so we can actually add a standard treatment. We can use path compression. So this basically we set the root of result to be the root of its root. So basically self root result, and then we're going to apply this self root again. So if we like, actually we can apply more times self root, but it plays the role now. So then we're going to return the result. So the reason is that after the while loop, or after we exit the while loop, we're arriving at a state that is result equals the root of result. Then we're going to return result. So this is a find method. So now let's look at the union method. The union method will accept two indices. So let's call them ig. Then here I'm going to use union by rack. So first, for the purpose of identifying if I and j are already in the same clusters or not, we're going to first find their root. So root I and root j. It's nothing but self find I, self find j. So then we're going to check if root I equals root j. If root I equals root j, we do nothing. Otherwise, we reset the root and update the rack. So if root I does not equals root j, we're going to track the rack information, then decide how to do the merge. So then if self rack root I is greater or equal than self rack root j, then we are going to set the root of root j to be root I. So self root of root j equals root I. And then we are also going to update the rack accordingly. So let's copy this line and then make modifications. So this increment corresponding to enlarge the cluster size represented by root I by the rec of root G. In other words, we add together the two cluster size because this is mimicking a merge. So in the other case, we're going to do the same, but in the reverse direction. So let's copy these two parts, two lines, and then we do the modification. Let's change this one to be I, this one to be G. Similarly here, we increment the rec for root G by that of root I. So that's the full implementations for the find and the union. So for our problem at hand, we are going to track the cluster information. So let's write a small hyperfunction called getClusters. So just for convenience, let me initialize a empty dictionary. The final state of this dictionary will represent the clusters. So we are going to iterate for kv in self root items. First, we need to find the root of the v, right? So let's see. Let's call it parents. So it's self find of v, and then we are going to check if the parent is already in D or not. If parent not in D, we're going to set the value for the corresponding to this parent as a single element set. Otherwise, we're going to add the current element to the set. So that's it for this hyperfunction. We're going to return D. So if we call this function after we set the final state of the data structure, then we can get the clusters. So with that said, we finished the first plan, that is to implement the data structure. So now let's look at the problem itself. So this is very routine once we have our tools. So first basically is to merge indices that can freely swap. So basically corresponding to use the union function to form clusters. So first I'm going to instantiate DSU object, and then we're going to iterate over the pairs. So for AB are indices, right? So for AB in pairs, so we're going to union them, union AB. That's all the main work we need to do. Then after this, we have set the final state corresponding to this current problem. Then let's get the clusters. So it's equals DSU get clusters. So then we are actually ready to build the final output. For that, let me first initialize a dictionary. So we want to build a lookup table. So now we iterate for the clusters. So for cluster in clusters values. So clusters is a dictionary. So we are interested in the groups represented by the indices. So then the characters corresponding to this cluster is basically SI for I in cluster. So here I'm using list rather than set because sometimes these characters can be the same. So then we're going to sort this one, sort it, so that we can get the lexical smallest one. So also the corresponding indices, I need to sort that, just sort it, the cluster. So then once we're done, we get the correspondence between the character and the indices. So for convenience, I'm going to build a lookup dictionary. So for IDX and for character in zip indices and characters. Then DIDX will corresponding to the character. So this way we have already made the thing aligned to the problem requirement. So next we just verbosely get the result. So for that we initialize a result variable which at the first is an empty string. So then we just iterate for I in range length of s. So for each index we set the correct letter or character. So if I in this dictionary, then we're going to update the result by adding the corresponding character in D. Otherwise, if I is not in D, it means that the corresponding character does not come into play for the swapping. So we're going to leave it as it is in the string, original string, right? So that's all the process, and now we're ready to return the result. That's the full solution code for this problem. So the structure is as follows. We first implemented a disjoint set data structure with two main methods. One is find, the other is union. And also we implement a hyper function called getClusters. After that, so we do the solution. First, we merge indices that can free swap, and then we build output. In the process of building the output, so there are some sort operations, and then finally we return the result. So with that said, let's check a special case first. So yeah, it passes this special case. Now let's do a generic case check. So let's do it again. Yeah, so with that said, I guess this finished the part 2 of the plan. So if you are only interested in the solution so far, so that's about it. So now let's basically do a quick temp complexity analysis. So the main temp is consumed here. So this for loop, we're going to do sort. So after we cluster the indices, it forms certain number of clusters, and then we sort each of the clusters. So let's look at the analysis. So assume that the cluster sizes are K1, K2 up to KL. So we know that the summation of all these cluster size will be less or equal than n. The reason is that some indices does not come into play for the swapping. But without loss of generality or get an upper bound, we can assume without that the summation of this cluster size equals n. So where capital N will be the length of the string s. Then the main temp is in the sorting. So here we're going to make these computations up to a constant, or you can say we're using big O notation. So for the sort, each temp basically is a k log k operation. Then we sum all these times used in sorting each of the small clusters, that is ki log 2 ki. Then we do the summation. So in order to make connections with this capital N, so in the first equality, we're minusing this n log n, then plus this n log n. Nothing changed, right? And then in the second equality, we're writing this capital N as a summation of ki, right? Then we want to group the first two terms together. So notice that I'm using a up to a constant symbol. So also I changed this log 2 to just any valid base log. So the first two terms together will give something like ki times log ki minus log n, then plus the remaining term. So the difference of two logs is transformed to the quotient, that is summation ki logarithm of ki over n, then plus this n log n term. And then for the first term, we're going to divide by n and then multiply by n. So nothing changed, right? So we get n summation ki over n logarithm ki over n plus the remaining term. Then we're going to add a negative sign in front and then add another negative sign, which remains the original formula or the expression unchanged. So if we look at the expression in the parentheses, so this guy is nothing but the entropy of a probability distribution. So the probability distribution is k1 over n up to kl over n, because each of them is non-negative and the summation is 1. So the time complexity is nothing but n log n minus n times the entropy of this partition entropy. So in other words, it's bounded above by n log n if we just to make a rough bound. So more precisely, the real time is given by n log n minus n times the entropy of the corresponding partition subject to a specific problem. So that's about the time complexity analysis. Let's come back to the original problem. So I guess with the time complexity finished, that's all about this video. So actually this code can be simplified, and you are encouraged to try, and also you are encouraged to check out other videos in this channel to look at different implementations specific to specific problems, I would say. Thank you very much.